Hey guys, Ms. Peterson here, and welcome to the physics lecture on measurements in science. In this lecture, we're going to be talking about accuracy and precision in how we make measurements in science, as well as metric units, scientific notation, and just some different ways that we represent numbers. So, what is precision in a measurement? Okay, so in any type of science, we can only make numbers as precise as we have measuring equipment to do it. Okay, our precision is determined by our equipment, and the typical rule is all known plus one estimated, meaning that every digit of the number that you know for sure, you can write down, and then you can estimate one more digit. So if you're on a ruler that has lines for every millimeter, you can estimate down to the 10th of a millimeter, okay? One more decimal place. Now, we also will use the words accuracy and precision when talking about our measurements. Accuracy is just how close to the actual number it is. Okay. Precision refers to how exactly we know a number, how many decimal places we know it down. So if we look at this image here, okay, we always want our measurements to be precise and accurate. We want them all to be plus or minus just a little bit of what that actual value is. But sometimes we can have very precise measurements that aren't accurate. Maybe a piece of equipment was calibrated wrong. Maybe I was using this ruler and it had worn down so that a whole centimeter of it was off. And so it was measuring everything a centimeter off. Okay? That's how we can have precise measurements that aren't super accurate. Now, if we don't have a super precise measuring device, we can be accurate, but not as precise. We're all within 1 centimeter of what it really is, plus or minus a bit more variance in the measurements, okay? So that's precision and accuracy. What would the measurement of this red bar be if we measured it as precise as possible? Well, let's look at it, okay? We have our centimeter ruler. We have that line for 2 there, and then right here, we have a line for 2.3. ¿Por qué no? Okay, so let's look at this. If we're looking for the measurement of this red bar, we can see a line right here for 2.3 and a line right there for 2.4 centimeters. So that tells us that we can estimate one more digit. We know it's between 2.3 and 2.4 for sure. So maybe we say 2.35 centimeters, okay? With that 5 being our estimated digit. Now, I couldn't look at that and say, you know, I think it is 2.3481 centimeters. Okay? Nobody else would estimate that. Hey, we can't estimate that many digits. There's no way I can know that. We can estimate one digit. So this number is precise to 2 decimal places. Okay, the nearest thousandth of a centimeter. It has 3 significant digits in its measurement. Okay, cool? Okay, cool. So, in physics, we're often going to be working with really, really big or really, really small numbers. Now, scientific notation is just a method of writing that in this format, A times 10 to the B. Now, when we do this, A will always be a number between 1 and 10. And B is the exponent. It's how many times you either have to multiply or divide that number in order to get your actual answer. You're in standard notation. Easiest way to handle this is if it's a positive number, positive exponent, that means we have a big number, greater than 10. Where if we have a negative B, that means we have a small number, less than 1, okay? If the number was between 1 and 10, then it would just be 10 to the 0, which is just 1. So there'd be no change to the number between it in scientific notation and standard notation. But for really big numbers like 5.97 times 10 to the 24th, okay, we wouldn't want to write that. We would have to do 5.97 times 10 24 times. Okay, the effect of that is moving the decimal over 24 times. So we can see that here. We started with it there, so right there in that number, and we moved it 3, 6, 9, 12, 15, 18, 20, 24 times to get our answer. Okay. So this is scientific notation mode, and then this is standard format, regular format, whatever you want to call it. Now, when using your calculator, you're going to be looking for either the button EE times 10 to the n, or there's one other one, EXP. Okay, one of those three buttons will be used and mean times 10 to the. Now, I highly recommend using these buttons when typing scientific notation into your calculator. The reason is if you try to type it in like times, 10, caret, and do all of that by hand, if you're doing larger calculations and you're not super careful about your parentheses, your calculator is going to confuse the order of operations. So it's easier just to use the built-in button for it. Now, often you'll hear physicists talk about order of magnitude, okay? We have it to the right order of magnitude, or things were off by 3 orders of magnitude. That just has to do with the relative size of a number. And it matters, okay? Think about a person who has $10 versus $100, okay? $100, that's a different order of magnitude, okay? It's 100 times. Versus what about a millionaire? Millionaire, okay, 10 to the 6th, so 1 with 6 zeros after it versus 100, okay? 100 and a million are very different orders of magnitude of money. So we use that in physics as well. Let's look at some practice problems. So first, just writing things in scientific notation versus basic. We have 5,690 centimeters. We want to put the decimal somewhere that's going to create a number between 1 and 10. In this case, it'll go right in between the 5 and the 6. So it becomes 5.69. And then we have times 10. The exponent is how many times we had to move the decimal, aka how many times we have to multiply 5.69 by 10 in order to get our number. If there's no decimal place, we assume there's an invisible one at the end, and we had to move it 1, 2, 3 times. This number is bigger than 10, so it's going to be positive 3. So 5,690 in scientific notation is 5.69 times 10 to the third. What about the next one? Where would you put the decimal to create a number between 1 and 10? Well, I would put it between the 3 and the 4. So we have 3.84 times 10. Hey, wait, 0.000, that's a small number. So we're going to have a negative exponent. Negative how many? Well, it's how many times we would have to divide that number by 10, aka move that decimal. So 1, 2, 3, 4, 5. So times 10 to the negative 5 meters. Okay, cool. Okay, cool. Now, can you do math with scientific notation on your calculator? Now, when you're plugging it into your calculator, something like this multiplication problem, we have 3.0 times 10 to the 8th meters per second times 3.2 times 10 to the 3rd seconds. So we got the speed of light, okay, times if you want the speed of light for 3.2 times 10 to the 3rd seconds, which is, let's see, which is for a little less than an hour, okay? We would type it in as 3.0, and then you would want to type your science button, EE or whatever that is, times 10 to the 8th times 3.2 EE3. And when you plug that into your calculator, you should get 9.6 times 10 to the 11th seconds, and seconds will cancel out, and we'll be left with units of meters, okay? So I'm going to go ahead and show you guys what that looks like on a couple different calculators. Okay, so I'm going to show you guys how to do this on these 3 calculators, starting with just plugging in the number. So let's go ahead and plug in 3.0 times 10 to the 8th, which is the speed of light. On this calculator, it's that EXP button, and it doesn't show the times 10 to the. Where on this calculator, E means times 10 to the, and I have to hit the second to get to that EE, times 10 to the 8th, and it does show the times 10 to the 8th. On this calculator, it will also show the lowercase e using that exponential notation. Yep. So if we wanted to see that in standard notation, we can change the mode. On this one, we can just change the mode to normal, from psi to normal, and then you have to quit the mode, and we can see now that number in standard notation. On this calculator, it's second and then this psi English, and we can change it back to flow to get that number in standard notation. And then on this calculator, it is this FE button. I don't know what the F stands for, but the E is for exponential notation. So if I press enter and that, I can get it to switch between. Okay, so I'm going to go ahead and change them all back to scientific notation mode. And we can do the math then. Okay, 3.0 times 10 to the 8th times 3.2 times 10 to the 3rd. And we get 9.6 times 10 to the 11th. On this one, I just have that answer there, so I'm just going to go ahead and press times. That'll do answer, aka your previous answer, times 3.2 times 10 to the 3rd. 9.6 times 10 to the 11th. And on this one, 3.0 times 10 to the 8th times 3.2 times 10 to the 3rd, 9.6. Again, it doesn't show the times 10, but we do need to know it's there. This is 9.6 times 10 to the 11th. Okay, cool. Okay, cool. So what is the metric system? Okay, we're going to be using the metric system a lot in this class. And all it basically is a universal system of measurements, which consists of a base unit and then a metric prefix, which changes that order of magnitude. Okay, it's not too different from scientific notation, really, especially if we're looking at it like, nope, that's not what I wanted. I wanted a highlighter. So we have our base unit. Okay, that's the 1, the times 10 to the 0. The ones that we're going to be using the most are centi, which is a hundredth. Okay, the way you think of this is just think of cents. A cent is a hundredth of a dollar. There's 100 cents in a dollar, so there's 100 centimeters in a meter. Okay, and then we have milli, which is a thousandth, aka times 10 to the negative 3. So if you have a millimeter, that means you have 1 times 10 to the negative 3, or a thousandth of a meter. And then kilo, easy way to remember that is think of your 5K likes on Instagram. If you got 5K likes, that means you got 5,000 likes, because kilo is the metric prefix, which means 1,000, aka times 10 to the 3rd. So 1 kilometer means 1 times 10 to the 3rd meters. If you get 2K likes, you have 2 times 10 to the 3rd, or 2,000 likes. Okay, cool? Okay, cool. Sometimes I think it is fun to look at the upper ones here. For example, when I've bought my first iPod, okay, it measured it in kilobytes, okay, how many kilobytes of storage it had. And then eventually we started measuring it in megabytes, or million of bytes, times 10 to the 6th, okay. Now we're in the gigabytes, okay, how many gigabytes is your phone? Giga meaning times 10 to the 9th, or a billion bytes of data. And you might even pay for storage on some hosts, which hosts a terabyte of storage, which is a trillion, or times 10 to the 12th bytes of storage. Okay, cool. Okay, cool. Let's look at some examples. Oh, I I do like putting this into the bigger context of why it matters, so I highly recommend you check out this TED Ed video on why the metric system matters. I will link it in the description. So let's look at these examples. Okay, how many kilometers is 7,380 meters? Well, I'm going to start with my known. Okay, 380 meters. Oops. Pen. We'll go with blue. Okay, there's my known. And I'm looking for kilometers. So I need to know the relationship between meters and kilometers. And I know that 1,000 meters is the same as 1 kilometer. So if I have 7,380 meters, I want the meters to cancel, so I'm going to put the 1,000. Oh, I tend to use this notation, but all it means is times and then a fraction is 1 kilometer. Now, 1,000 meters and 1 kilometer, those are the same measurement. They're the same amount. So you can really think of it as you're just multiplying it by 1. Okay? You're not changing its value, just its units, which is what we want. So we have meters and meter units cancel out. So we're left with units of kilometers, which is cool because that's my unknown. And then I have 7,380 times 1 divided by 1,000, which gives me 7.38. AKA you're just moving the decimal over 3 times. And this makes sense, okay? Kilometer is 10 to the third meters. So if we put 380 meters in scientific notation, it would be 7.38 times 10 to the third meters, okay? The prefix kilo just means times 10 to the third. Okay, cool? Okay, cool. Let's look at the next one. Okay, how many meters is 2,467 centimeters? So again, I'm going to start with my known. 2,467 centimeters. Okay, so we have 2,467 hundredths of a meter. I know that there are 100 centimeters in 1 meter, so I'm dividing it by 100. AKA just moving that decimal over 3 times. So 2,467 centimeters is the same thing as 24.67 meters. Okay, cool. Okay, cool. Now, what I just did, especially this little like train track thing that I tend to do, is just an example of unit analysis. That's a method of solving problems that we'll use a lot in this class that focuses on the units. Okay, you always have to start by identifying your known and unknown, find inequalities or the relationships that can relate those two things, and then we set up the problem so the units cancel. So the format will always be known, and then again, I tend to do times in a line, and times in a line, and times in a line if I have like 3 conversion factors, but the shortcut form of that is to just do it like this. So we have our conversion factors here as fractions. Okay, so these are fractions / equalities, okay, where the top and the bottom are equivalent to each other. And that should always equal our unknown units. Okay, cool. Let's look at this in an example and make a little bit more sense. Say we have to convert 65 miles per hour, which is how we normally measure our speed in cars, to metric units, meters per second, which is how we'll normally measure speeds in this class. What would that be? So I'm going to start with my known. Now, you guys don't need to know how many miles are in, how many meters are in a mile or that. I'm just going to go ahead and tell you. 1 mile is equivalent to 1,609 meters, or 1.609 kilometers. Now, let's go ahead. We have 65 miles per hour. That's our known. And then we're looking for meters per second. So we start with our known, 65 miles. And then per in physics, in math, always means divided, or like a fraction. Okay, 65 miles per hour. Per how many hours? Well, per 1. Okay, that 1 is assumed to be there. Whether or not you put it there, it doesn't really matter, but we know we're going 65 miles per 1 hour. We're going to need that hour there because we also have to convert it to seconds. But let's deal with the distance first. So I want the mile to cancel out, so I'm going to put 1 mile on the bottom and then 1,609 meters on top. So right now, the miles units and the miles units cancel out. I could solve it out, and I would know how many meters per hour the speed is. But I want to note in meters per second. So now I need to convert the hours to seconds. I don't know how many seconds are in an hour off the top of my head, but I do know how many seconds are in a minute and how many minutes are in an hour. So I'm going to use 2 factors for that. I want the hour to cancel out, and I want these seconds to end up on bottom. So I'm going to do 1 hour is 60 minutes. Note, when you're doing these conversions, always make sure that what's on the top equals what's on the bottom. A common mistake is doing things like 60 hours is 1 minute, and that doesn't make sense. We know 1 minute isn't the same thing as 60 hours, but 1 hour and 60 minutes, those are the same. So we have that, and then 1 minute is 60 seconds. Checking our units, okay, we can see the hour on top cancels out with the hour on bottom. The minutes on top cancel out with the minutes on bottom. And so then we plug it into our calculator, and we get 29 point something. We only have 2 digits there, so I'm going to round this and just say 29, and the units are meters over second. Meters per second. And that's how we can use unit analysis to solve these problems. And that's it for the lecture. Okay, cool. Okay, cool.